So there are three problems. All are only one answer is correct in each problem. And you have 2 minutes to do. One minute left. Okay, I will be giving 30 more seconds from here. We are in extension time. Ten more seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1. All right. Okay, let's look at it. Let's start with problem 1. Can you see the poll results? Jared, you are on top of my screen. Can you see it, Jared? Can you nod your head if you see it? Great, thanks, Jared. Okay. In a constant composition system, in all the problems, the highest percent answer, 70% got it right, 13% got it. So the highest percentage who got it right is correct. In the first problem, we have mentioned multiple times that U could have been written as a function of pressure, volume, temperature for a constant composition system. When it's constant composition, why would you think N would be a variable? I don't know. So N is out of the question for that reason. And then we say that this could have been UPVT. It could have been UPV, UVT, UPT. And we mentioned that these are the natural variables for this system. And you can remember why this might be the case, because first law of thermodynamics says that du is equal to dq plus dw is equal to dq minus pdv. And when dv is equal to 0, du is equal to dq. So there is something special about internal energy and constant volume processes. That's why V is a natural variable. Later, we will visit this from a more mathematical perspective. If I'm allowed, man, you guys will all want me to do just problems. So maybe we will not do any concepts at all. So for that reason, VT are the natural variables for U. For H, through a similar argument, we saw that H corresponds to dQ at constant pressure. This was at constant volume, and dH corresponds to dQ at constant pressure. Therefore, P was a more natural variable. And 70% of you got it right, which is good. Second problem is, if I wasn't depressed last evening, now you totally have me depressed. How is this possible? This is exactly same as the pop quiz question from last time. Heat change, constant pressure is delta H. Heat change, constant energy, constant volume is internal energy. I mean, so again, I'm trying to emphasize, if these concepts are wrong, as we can see in this pop quiz, how would practice problems improve your grades? I don't know. Okay, I don't know which one is making me more sad, problem 2 or problem 3. If a function f is a state function and the function g is a state function, then f plus g is also a state function. Thus, and in fact, we mentioned that when we said that h is a state function, how did we reach that conclusion? We said, well, u is a state function, and to u we are adding pressure and volume. Pressure and volume both are state functions. Therefore, sum of these two state functions is a state function. And the same idea applies to h plus u or h minus u or h plus e to the power u or h plus cosine of u, whatever you want to do, or sine of h minus arc cos of h, as whatever complicated thing you want to come up with, it's a state function. Okay, any questions about this? So, okay, now let's get to I'm going to screenshot these. So the next time someone blames me for not giving extra only practice problems is not the problem in this class. If I'm going too fast, please stop me and ask me to explain concepts. Okay. All right. Any questions? No question is a bad question, okay? Please stop and ask me. I have no problems in explaining things. And otherwise, let's start with today's class. So today, we are going to talk about a particular class of change, which is very common across physical systems, across in laboratories, in real life. It's easy to control, and it is called an adiabatic process. So what does adiabatic process mean? We visited it very briefly in last class when we were doing the Joule-Thomson coefficient, and we had that whole box which was thermally insulated. So an adiabatic process is one that happens without exchange of mass or heat from the surroundings. So it's a thermally insulated system. You can make it in a tight, some sort of a furnace, which is really isolated from everything else. So it's of course, in real life, there will be some leak happening of one form or the other, but I think it happens. It's not that hard to make. So what does this mean for us in terms of the things that we have been looking at? This means Q is equal to 0, right? The heat given to the system is 0. So what do we know about delta U? Delta U we know that delta U is equal to heat given to the system. We can call it delta Q, or we are just calling it Q, plus the work done on the system. So for an adiabatic process, since Q is equal to 0, we have delta U is equal to W. We call it as the W adiabatic. So we are interested in, the adiabatic expansion of a gas. So we have a gas which is in a thermally insulated container. The whole container, it's a chemical reaction happening or something going on. In this case, it's just the gas expanding in a thermally insulated container. So let's consider expansion of gas in a thermally insulated container. And the question we ask here is, how do the temperature and pressure change as a function of the volume of the gas? So we started with the gas over here. Let's say it had some volume VI, and we just let this move and the gas take up the full volume VF. So the gas moves from VI, V initial, to some volume VF. Expands from VI to VF. So the question is, how do temperature and pressure change? So a lot of thermodynamics, your homework 3 and your midterm problems will have questions in the same category. So what I'm doing right now might look like a derivation to you, but if you understand what I'm doing right now, many of the problems will be trivial. And when I say trivial, I really mean trivial, not like a mathematician's trivial, which means, so a mathematician's trivial is, I got to make a joke about mathematicians. So a mathematician's trivial is when they go and argue for 3 hours and they come back and say, oh yeah, it's trivial. You know, if they can, if it can be proved, it's trivial as per a mathematician. But this is not a mathematician's trivial. It will actually be easy if you understand what we're doing now. So Liam asks, is W adiabatic equal to the work done on the surroundings? Yeah, so we have always defined it's work done by the surroundings, right? This is what we have always defined our W as. So in this case, U is the internal energy change of the system. Q is the heat given to the system, and W is work done on the system, right? So this is adiabatic work done on the system. So another way to think of it is, even though we have a thermally insulated container, the volume of the container can go up and down, right? That's the whole idea over here. Hope that answers your question, Liam. So how do temperature and pressure change in this case? So let's go through it carefully. And this is, I like this derivation because it puts into use many of the things we have seen so far. So let's go through it slowly and carefully. So the work done delta W, let's look at it in a differential form, okay? The work done delta W is going to be minus PdV, right? That's always true. We are thinking only about expansion work. So du is going to be delta Q plus delta W is equal to delta W. Why is this true here? Because we are looking at adiabatic process, right? This will not hold true for generic processes. For generic processes, delta Q will not be 0. It's an adiabatic process, therefore delta Q is equal to 0.
I'm sorry, Professor, can you explain what the sign mean? Because I don't know if that's an F. I don't know if that's an
Which one?
The sign that looks like an F.
Let me draw a line and you tell me where to stop.
The delta with the line through it.
Delta, yeah.
This one?
Yeah.
Let me, is the culprit gone now?
Yeah. Like, I just don't know what the symbol represents.
This is, oh, I see what you, I see, I made my own symbol, sorry. I mixed both of them. You're absolutely correct. Sorry about that.
It's okay.
No, it's totally, I created a new language. It's called Greek plus French equal to freak. How about now?
Yes, that's much better.
Sorry about that. Yeah, like you did. That's perfect. Please stop me anytime I do anything funky, which I can do many times. So this is equal to 0. Therefore, du is equal to delta W. Now, this is true in general, right? So far, we haven't assumed anything about an ideal gas. It's a closed system process. So as Elizabeth Engel wrote down, adiabatic is a closed system process. Exactly. So it's a closed system means closed both to heat and mass. Nothing is changing. Okay. Let's look up what Atkins says about it, just to make sure when you go back and read Atkins, you don't get confused. Let's see what Atkins has to say on this. Page 67. Well, I'll clarify with Atkins later, but what we have here is correct. It's a closed system process. Closed system means mass and energy both. So it also means Q is equal to 0 because heat cannot, so it implies Q is equal to 0, but it's not just that. It's a closed system process. So we have, so where were I? Where was I? At this point, let's further assume, let's focus on ideal gas. So the things that I'm going to do next are going to be specific to ideal gas, but if you pay attention here, when I give you a homework problem where I ask you to do the same thing for van der Waals gas or some other gas with a different equation of state, the procedure will be similar. It won't be identical, it will be similar. So just see how it works. So for ideal gas, let's try to write down du.
It looks like the
It
screen might be
disconnected.
disconnected.
Yeah, sorry about that. So for an ideal gas, let's focus on an ideal gas and let's write down our du for an ideal gas. Again, we know the natural variables to think about u are v and t, right? So we can write it down as partial u by partial t at constant v multiplied by dt plus partial u by partial v at constant t multiplied by dv. For an ideal gas, we know, well, that this term is going to be 0, right? Is everyone happy with that? If you're not happy, just send a chat message, say I'm unhappy, and I will try to explain it. But it basically comes from the fact that for an ideal gas, u is simply something like half nRT, right? There is no volume term. Sorry, okay, Katie, let's try to make you happy. U for an ideal gas depends only on temperature. It does not depend on pressure or volume. It's only true for an ideal gas. For an ideal gas, U does not depend on pressure or volume. Therefore, when you differentiate it with respect to volume, the derivative is 0. That's why hopefully you're less unhappy now. This one at the same time is CV. It is the heat capacity at constant volume. That's the definition of CV multiplied by dt plus 0. So for an ideal gas, du is equal to CV dt. This is an interesting relation. It looks almost like for a generic gas, what would we have had? We would have had CV is equal to partial u by partial t at constant v for any gas, right? For an ideal gas, we can replace these partials with the total derivatives. I didn't write du is equal to 0. I said partial u by partial v at constant t is 0. This thing is 0. Du is equal to cv dt. So again, u for an ideal gas, u ideal is a function only of temperature. That's the thing to remember. Okay, that's where we got this from. This is not going to be true in general. This is true only for an ideal gas. So if you were to derive this for a van der Waals gas or something like that, the derivation will be different from this point. So for an ideal gas or for a perfect gas, we have du is equal to Cv dt. We also, however, have the ideal gas law, right? We have P is equal to nRT by V. Therefore, let's try to actually number equations at this point. It will make our life simpler. So we have du is equal to Cv dt, and we have P is equal to nRT by V, equation 2. Okay, so let's flip the page. And equation 1 implies du is equal to Cv dt is equal to delta W, right? Because delta Q is 0. It's always adiabatic, but now we are looking at adiabatic for an ideal gas. We are focusing on adiabatic, but I made it even a bit specific, trying to talk about only about ideal gas. And this is equal to minus PdV, right? Equation 3. So Cv dt is equal to minus PdV. And equation 2 says P is equal to nRT by V. So therefore, Cv dt is equal to minus PdV. And in this, if we use equation 2 and we put in the value of pressure, that is nRT by volume, right? So this is minus nRT by volume multiplied by dV using equation 2. Therefore, Cv dt by temperature, this temperature we are going to bring here in the denominator, Cv dt by temperature is equal to minus nR dV by volume, right? Equation 4. I've just done a slight rearrangement. Yeah, this is why I bought a bigger iPad, even though I'm totally broke now, so I don't have to flip pages, but sometimes I still have to. So now we can talk about the change in temperature as we go from one volume to another volume, right? What did we do over here? Here we went from volume VI to VF. And the question we wanted to answer is if we have a container where we are doing work on the system but otherwise the system is closed, it cannot exchange any heat or any mass with the surroundings, what's going to be the change in the temperature? So this change can now be integrated on the left side, Ti to Tf minus nR Vi to Vf dV by V, or Cv ln Tf by Ti is equal to minus nR ln Vf by Vi. Let's rearrange this, and we get Cv by nR ln Tf by Ti minus ln Vf by Vi, right? So let's define this Cv by nR. This is something, it's heat capacity divided by N divided by R. Let's call it a name. Let's give it a name. Let's call it C. We define C. It's not the speed of light. It's just a letter C. Denote that. Which is Cv by nR. So what do we have now? We have C ln Tf by Ti is equal to minus ln Vf by Vi. Therefore, this C can go into the power here. So therefore, ln Tf by Ti to the power C is equal to minus, and this minus can go in here, ln Vi by Vf. And we get an interesting relation. If we now remove the logs from both sides, we get Tf by Ti is equal to Vi by Vf to the power 1 by C, or Tf is equal to Ti multiplied by Vi by Vf to the power 1 by C. We have a little nice, beautiful relation only for an ideal gas. Sadly, it's not going to work for a real gas. I invite you to go and think. Should I say that? One of the persons wrote in the farm, do not invite us to go and think. I'm still going to invite you to go and think. I cannot judge my decision on the basis of one person. I think it's a good thing to go and think. You should go and think. It's the nature of learning. Please go and think. How would this look like if this was not ideal gas? If you had some other equation of state, how would this look like? Yeah, please go and think. So this is how the temperature would look at the end of the process if you had expansion. This could be expansion or contraction, right? Vf could be more than Vi, Vf could be less than Vi. Let's see how would it look like for expansion. For expansion, Vf is more than Vi. And C is positive, right? Because we know that heat capacity is positive. So if Vf is more than Vi, then what does it mean for Tf? Is Tf going to be more than Ti or less than Ti? What do you all think? And does it make sense?
Less than?
Do you see it from the math? Let's say C is equal to 1 for simplicity. And Vf is more than Vi. So then Tf should be
Less than
Ti. So does that make sense though? We expanded the gas and the temperature went down.
Yeah, that makes,
Does that make sense?
well, yeah, because molecules are less clustered together, so there's less kinetic
Okay.
energy being bounced around.
Okay, good. So we can write it down in a more compact way. We can write it down as Tf Vf one moment, something's puzzling me. Yeah, so if we take power C both sides, then we get Tf to the power C is equal to Ti to the power C multiplied by Vi by Vf, right? Now we can write it down as Vi Ti to the power C is equal to Vf Tf to the power C. In other words, Vt to the power C is equal to constant for adiabatic expansion or contraction of ideal gas. This is one of those, yeah, the C by C, and it's well, Zoom doesn't allow really using subscripts or things like that. How does temperature change if heat cannot be exchanged with the surrounding? Well, you're doing work with the surrounding, right? That's the funny thing about temperature. Temperature looks like it should change with the heat, but temperature is more than that. The internal energy of the system is changing. Temperature changes because we are changing the internal energy of the system. That's why it changed. So this expression is something which will show up again and again. It's kind of hard to derive. In this semester, we are all doing everything open book and everything, but it's something that you should, if you had a cheat sheet, you should write it down. It's worth noting this expression. For many problems that we are going to encounter later, you will have, we are going to look at these things called the Carnot cycles and things like that. And there, if you remember that Vt to the power C is equal to constant for an adiabatic expansion, it will save you some time. Especially if you're going to take GRE or MCAT or one of those things, it's a useful thing to remember. Yeah, so precisely, work is still being done here, like Kevin said. It's the work that is going into, it is this work that is leading to internal energy change. if delta Q was 0 and delta W was 0, then of course temperature cannot change. We have no solution to that. Actually, even then temperature can be changed if the kinetic energy and potential energy are talking to each other. But in this case, the thing to keep in mind is that work is being done on the system, so definitely temperature can change. So we just derived this. What did we derive? We looked at how the temperature changes with respect to volume in an adiabatic process. Now let's look at pressure. How does the pressure change? It shouldn't be too hard. The reason it shouldn't be too hard because we know the ideal gas law. We know PV is equal to nRT. So we can just plug in the value of temperature that we just derived and get the expression for that. So what does this mean? This means that PI VI, pressure initial, volume initial, by pressure final, volume final, is going to be TI by TF, correct? And we just derived a relation for TI by TF. We showed that TI by TF is VF by VI. We just showed that TI by TF is VF by VI to the power 1 by C. Right? We bring the VF to the numerator on the left and VI to the denominator. So this thing is VF by VI to the power 1 by C. Therefore, we just do a bit of rearrangement. PI by PF, VI by VF to the power 1 over C plus 1 is equal to 1. And now, again, we are only in ideal gas land right now. For ideal gas, we derived this wonderful, nice looking relation that Cp minus Cv is equal to Nr. Let's see if we can use that here to simplify things a bit further. So, and talk about the constant C. So what does it mean for the constant C? This constant C, which we have been dangling, it is 1 by C plus 1 now. What is that? That is the same as 1 plus C divided by C. What is 1 plus C? Remember what was little c? Little c was Cv by Nr. So this is 1 plus Cv by Nr by Cv by Nr is equal to Cv plus Nr by Cv. What is Cv plus Nr? That is Cp. That is Cp by Cv. And this ratio of heat capacities has a name. We call it gamma. Gamma is defined as, it's just a shortcut. Gamma is equal to Cp by Cv. So what do we get now? We get Pi by Pf, Vi by Vf to the power gamma. So the message here is that 1 by C plus 1 is equal to Cv plus Nr by Cv, which is Cp by Cv, which we call it gamma. So this whole thing is gamma is equal to 1, or Pi Vi to the power gamma is equal to Pf Vf to the power gamma, or Pv to the power gamma is equal to constant. This is also an important relation to remember. And they kind of look similar. Again, this is adiabatic and ideal. Gamma is equal to Cp by Cv. So what did we derive so far? We derived Pv to the power gamma is equal to constant for an adiabatic process. And for that same process, Vt to the power C is equal to constant, where C is equal to Cv by Nr. So these two relations are quite important for the simple reason that adiabatic changes are quite common in thermodynamics. Any questions about this?
Is that one equation PIVI to
Again?
the power of gamma? Is that one equation PIVI to the power of gamma equals PFVF?
To the power gamma.
Okay.
Yeah, so I just took this one and rearranged it. PIVI to the power gamma. And then I took this PF VF to the power gamma and brought it to the right hand side. It's just rearrangement. It looks Greek, but well, there is gamma, which is Greek, but it's
Okay, thank you.
Okay, so now what I want to talk about very briefly is a bit of thermochemistry. The reason I want to talk, last bit is to the power of C. Yeah, that's correct, it's to the power of C. I want to talk about a bit of thermochemistry and send you off to read a section from Atkins if you're interested to learn more about it. It's not complicated, but it gives you a bit of sense into how these things are done in experiments. Once we finish thermochemistry, we will start with second law of thermodynamics. And for those of you who think that there is a divide between concepts and practice problems in thermo, the divide's gonna get worse starting next class. Second law of thermodynamics, things get fundamental. They get very basic. What is the meaning of entropy? What is the meaning of heat? What is the meaning of temperature? There will be different statements of second law of thermodynamics. And we will be trying to think about that. Turns out entropy, which is a term that many of you have heard, is actually a bit complicated to understand, but we will develop that understanding. We will first get collectively confused, and then we will solve that confusion. It is, however, much harder to prove that entropy is a state function. And it's a wonderful proof, and I like it a lot. Hopefully you will also appreciate it, that entropy is actually a state function. Proving enthalpy is a state function was trivial, right? Because it was just U plus PV. We took a state function and added another state function to it. Entropy is not defined that way. Entropy is not defined simply from what we have right now. It takes a new law to think about entropy. And that's the second law of thermodynamics, which is something we will start next week. So we will go through second law of thermodynamics. We will stop at some point. I have a specific point in mind where I want to stop before the midterm. I don't want to go too far beyond that. Once we stop there, we will take more time to discuss what we have done so far. That doesn't mean me solving practice problems and you just looking at it blindly. We'll do a little bit of that, but I also want you to ask me questions. You can post questions on Slack or everything, whatever has confused you so far, conceptually or in any possible way, and we will work through that. So let's do just a bit of thermochemistry. We'll start today, do a bit more on Monday, and then starting Monday, we will move to second law. So thermochemistry, and some of you said in the forms to refer to Atkins sections or chapters. I don't do it by the name because section addition to addition that changes. But if you look at this, the topic headers that I use are very, very similar to Atkins. If you look at the topic of contents, a table of contents, they have specific sections, for example, titled Change in Internal Energy with Pressure. So if you go and look up my notes and try to cross-reference, and I'm moving almost in a linear manner, almost. There is a bit of a back and forth, but it's not as bad as Pakoda going from point A to point B, because he never walks in a straight line. It's, his motto for life is, let's get from point A to point B in the most complicated, funkiest possible way I can. Out for a walk, or I would have shown him to you. So thermochemistry is really the study of heat. You know, as the name says, in a certain way, it is the study of thermodynamics in the lab. And it allows us to measure all these things that we have been talking about. It so happens that enthalpy is typically the easiest thing to measure in thermochemistry for the simple reason that constant pressure experiments can be done, well, maybe constant volume or so. Either we measure enthalpy or internal energy. And now we have all these wonderful relations that we have derived that allow us to move back and forth. We measured something under constant pressure. We have our power of thermodynamics to go and look at it, modify it, and try to think about how would it have looked if it was a constant pressure process, for example. So we can change all that. And especially in thermochemistry, we study chemical reactions happening under a certain set of, my screen is frozen, it's terrible. So we are going to think about chemical reactions, and we can classify in them in many different ways, right? So one simple way to classify chemical reactions is whether they consume heat. So if the reaction is our system, what would this mean for Q? If a reaction consumes heat, would Q be positive or negative? What do you all think?
Positive.
So if a reaction consumes heat, that means the surrounding has given heat to the system, correct? That's your, I think that's correct. So Q more than 0. And if it produces heat, then Q less than 0. This is in our nomenclature. You could have followed the opposite nomenclature also, but then you would have to go back and rewrite your first law of thermodynamics to keep that into account. What are the examples? So, and this have a name. Such reactions that consume heat are called endothermic reactions. And reactions that produce heat are called exothermic reactions. Example of endothermic reactions are melting of ice. Example of exothermic reaction is freezing of water, the same thing in the opposite way, right? Example of another endothermic reaction is dissolving ammonium chloride in water. This is from the perspective of the system. Everything is from the perspective of what happened to the system. Surrounding is outside. We don't care. We care about the surrounding, but it is all, did the system consume? So remember, our first law of thermodynamics was delta U is equal to delta Q plus delta W. So we are trying to stay consistent to that. So, and freezing of water is an exothermic process. Dissolving sulfuric acid is also an exothermic process, which I'm sure some of you have experienced in the lab at some point, right? Probably in a type 3 fun type experience. I have, it was horrible. So thermochemistry is really the study of this heat that is transferred during chemical reactions. It focuses on heat. That's why this endothermic, exothermic classification is fundamental. But on top of this, on top of both of these, we could have a constant volume process, or we could have a constant pressure process. And I'm going to ask you this question again in the next pop quiz, and until and unless 100% of you get it right, I will keep asking it. At the end of the semester, if you don't remember anything, I would like you to remember, for a constant volume process, Q corresponds to change in U. For a constant pressure process, Q corresponds to change in H, that is isobaric process or isochoric process. I will keep asking you. Every pop quiz, there will be one question on this, I promise you. This is important to remember. It's a simple concept and it will make your life easier later. So if delta H, so let's think about this one, for example, the constant pressure process. And I'll shut down in a moment. I know I'm out of time. So if delta H is less than 0, it means the system produced heat, right? Delta H less than 0 and H corresponds to Q. It means Q less than 0. It means heat was produced. This has another name. In this case, it is also called an exenthalpic process, because enthalpy has been released into the system, into the surroundings. And if delta H more than 0, this is called an end-enthalpic process. If these names confuse you, you're not alone. I also get confused once in a while, but this is just good to have this written down somewhere, because you might have a problem in some other exam where you see these names and I don't want you to get stuck. So next time what we will talk about is enthalpy change. And the thing that we are going to use there really is that enthalpy change is related to, delta H is related to Cp. If we can measure the heat capacity at constant pressure, we can talk about the change in enthalpy. And we will also use the second property, which is H is a state function. In next class, when we do thermochemistry, you will see how the state function actually becomes very useful, because if you have a reaction where A goes to B, and then B goes to C, and then C goes to D, and you want to calculate the enthalpy change between D to A, you can simply write it down as HD minus HC plus HC minus HB plus HB minus HA. And you can do 3 separate reactions, A to B, B to C, C to D, and you can talk about the enthalpy change that would have happened in a frictional reaction going from A to D. This is possible only because enthalpy is a state function. And we will do this next time. So next time we will finish thermochemistry, which is quite fast. It's easy relative to what all the things we have studied so far. We will look at something called Hess's law, and then we will move to second law of thermodynamics. For next time, the readings the topics for next time are already on the website. Please go and look it up. And in Atkins' book, if you go to the table of contents, you can look up those topics. It's in the full contents, those topics are mentioned here. So just go and read that up. It will be basically second law of thermodynamics and thermochemistry. Thermochemistry will be 15 minutes, and then second law of thermodynamics we will start. And then we will be in solid type 2 fun category. Look, type 2 fun is hard. The fact that so many of you really cursed me in the forums is because you are having type 2 fun. It's a bit hard, but you will get there. Hang in, it will get easier if you put in hard work. If you are in the bottom 10 of the second homework, then you talk to me and see what can be done differently. We will be having office hours on Monday at 11 a.m. Okay, thank you.